Very good morning to all and welcome to my class. Today we are going to discuss chemical bonding, right? So far we are covered two chapters, that is mole concept, equivalent concept and structure of atom. So in previous class we are discussing about the structure of atom, right? So this class is totally based upon chemical bonding. Okay. So in this class we are going to study chemical bonding, some important topics which is important for the advanced point of view and try to do some PYQ question as well, right? So that you got an idea which type of basically questions are coming from this chapter, right? So let's start with the today's session, that is chemical bonding. Okay. I hope my screen and my voice is audible to you and my screen is visible to you all, right? Okay. So let's start the chemical bonding. I'm going to start this in a basic way. Now then we are going to proceed the way like doing questions related to whisper theory and VVT theory, right? So, what is the basic theory of chemical bonding? So basically, what do you need of chemical bonding? Why basically atoms combine to form chemical bonding and all? So these type of things you already studied in your 12th class and all, right? So formation of chemical bond and bonding in them arise many questions like why do atoms combine? Why are only certain combination are possible? Why only magnesium combined with Cl to form MgCl2? Why magnesium does not form MgCl3? So such type of questions were arise, right? In order to answer such question, different theories and concepts have been put forward from time to time, out of which some important are as follow. So we are going to study the Lewis approach or is the octet rule, because sometimes the questions were directly coming from this topic. So you know what is octet rule, right? So it should be better to know the octet rule and Lewis approach. So what are the main points of this approach? So main points are the outermost cell of an atom is called the valence cell and the electron present in it are called valence electron. So this is very simple and you know all these things, that is the outermost cell of an atom is called the valence cell and the electron present in it are called valence electron. Now the inertness of noble gas is due to their stable configuration, right? So the we know that 18th group or we say noble gases are inert. So why they are inert? They are inert because they possess stable electronic configuration due to presence of 8 electron except helium, because in helium it has 2 electrons, so it's so duplet, not octet, right? Now, on the basis of Kosel and Lewis proposed that element having 8 electron in their outer cell, that is having complete octet, are chemically inert. It means those having fully filled electron, those having 8 electrons are chemically inert and they are not useful for us, right? Because they're already stable. So they do not want to make any bonds and make any compounds and all, right? So hydrogen is the only exception which has a 2 electron. This is not hydrogen, beta. This is helium, right? So helium is the only exception which has a 2 electron in its valence cell. This is called popularity as octet rule. So I hope you understand what is octet rule. Octet rule means nothing but having inert nature and having 8 electron in their valence cell and become inert and become stable. This is called the octet rule. Now, element that do not have complete octet have a very high tendency to attain this configuration. It means those elements we have a deficiency of this octet. Either they have a less than 8 electron or one which having more than 8 electrons. So they want to stay. They want to gain this stability. They want to achieve this stability for either to do if some have having less of electron, they want to gain electron from the others. If someone having more than 8 electron, they want to lose electron to gain this stability of 8 electron, right? So all these are used as a means in bonding. So either by losing or gaining or sharing, these are only three things are possible. If someone having more electron, then it can lose. If someone having less number of electron, they can accept from the others. Or someone have tendency to share the electron as well. So three types of sharing are possible, either by complete losing, by gaining, and by sharing. Now, so in this, we have to say concept-based question like, if someone asks you how to draw, right, how to draw the CO3 twice negative ion, Now, how will you draw ozone molecule? And you have to calculate the Lewis dot structure. You have to calculate the lone pair bond pair using the Lewis dot structure. So how will you draw? So let's see for the ozone first. So we know that this is oxygen. In ozone, there are three oxygen, right? So we need oxygen having valency 2, comma 6. So oxygen having valency 2 and having 6 electron in their valence shell. Now, each one wants 8 electron to complete its octet according to the Lewis approach, right? So if one oxygen having 6 valence electrons and three oxygen, three oxygen having how many electrons, beta? 18 electrons, right? Now, out of this 80 electron, let us assume this will make a single bond and this will make a single bond, right? So how much electron they more require? This will require 2 electron to 4 and 6 and 6. It means they require 14, and this one requires 6 electron, right? And this one also require, I'll name it. This is oxygen number 1, oxygen number 2, and this is oxygen number 3. So oxygen number 1 requires 6 more electron to complete its octet because 2 electrons are already sharing here, right, between oxygen 1 and oxygen 3. So oxygen 1 requires 6 electron. Oxygen 2 also requires 6 electrons, so 6, 6, 12. Now this bond having, we know that one bond having 2 electrons. So this two bond having 4 electrons. So this is 6 and 6, 12, 4, 16. 16, and this one require more 4 electrons, that is 20, but we have only 18 electrons. So it is very much clear from this only that deficiency of 2 electrons is there. So either of these two, either oxygen 3 and 1 or oxygen 3 or 2 make double bond, right? So it will make double bond. Now you can calculate. Total we have a 18 electron. Out of 1 to 3 bond means 6 electron. So 18 minus 6, what left, beta? That is 12 electron. Now this oxygen having already 6 electrons because it formed 3 bonds. So 6 electron they already having. So it wants only 2 electrons, right? So they having only 2 electrons. So just subtract 2 here. So what left, beta? 10. This oxygen requires 6 electron, 2, 2, 4 and 2, 6. We have left with 4 electrons, and this oxygen exactly require 4 electrons, right? This will exactly require 4. So this bond is absolutely correct. So this is how we can draw the structure of O3, right? So we can draw the structure of O3. O3 also show resonance, right? O3 also show resonance. Sometimes this double bond shifted here, and they also make double bond, right? So they will form a resonance. Okay, just remember this. I hope this is clear to you. Okay. Now, this is how you will draw the Lewis dot structure. On the similar basis, if I'm talking about CO3, so C having the central atom, right? Now, for such a molecule, it is very simple to draw the diagram. We know that oxygen, normal oxygen having 2, comma 6 and its valency is 2, right? But oxygen, whenever some negative charge is given to the molecule, always assign this negative charge to the element which is most electronegative. So out of carbon and oxygen, which one is most electronegative, beta? Obvious oxygen. So this negative charge is developed to the oxygen only, right? So always remember this thing. Whenever the negative charge is given to the whole molecule, always assign this negative charge to the most electronegative element. Okay. Now this is O comma 26. So what is the valence electron of O negative? It will become 2 comma 7, right? So this will become 2 comma 7. So it requires only 1 electron. So out of these 3 oxygen, 2 having negative charge, right? So it will require only single bond. So this is single bond, and this one require double bond. So now octet of each atom is completed. So this is the structure of CO3, carbonium ion. It will also show resonance, beta. They will also show resonance like O, C, double bond. This is O negative. This is O negative. One more structure like O, C, O negative, O negative, and double bond O. So these three are the resonance structure of carbonyl, CO3 twice negative. I hope this is clear to you. If someone asks, you have to calculate the number of bond pair and lone pair in the oxygen or 1, 2, 3. So you can easily calculate. This will known as a lone pair. So oxygen one having how many lone pair they having? So lone pair is equal to 2. and lone pair of electrons means 4 because one lone pair consists of two electrons, right? Similar, oxygen 1 having bond pair, so it having bond pair of 1, right? It making one bond pair, or we say two electrons. So I hope this is clear to you how to draw the dot structure and all. On the similar basis, if someone asks how will you draw the NO2 negative, NO2 negative, how will you draw beta? We know that out of N and O, this is N, this is O, this is O. So one O having negative charge, it means they require only single bond and it will require double bond, right? So how the octet complete beta? We know that nitrogen having 2,5 electron in their valence shell. Out of 5, one electron is taken in this bond, single bond, and 2, 3. So lone pair, how much lone pair is formed? That is 2. Oh, so sorry. One lone pair also formed here, right? So for nitrogen, this is 2 to 4 to 6 into 8 electron completed octet, and for oxygen also octet being completed, right? So this is how you can actually draw the diagram of NO2, or we say NO2 plus and all. Similarly, if someone asks how to draw the diagram of NO2 plus, how will you draw beta NO2 plus? We know that this is N, this is O, this is O. So NO2 plus means what? We know that N having electronic configuration 2 comma 5. So now in this case, what they having electronic configuration 2 comma 4, right? So this will form double bond and double bond, and they having one positive charge, right? So this is how will you draw the structure of the following compound like CO3, O3, NO2 plus and NO2 negative. I hope this is clear to you. Anyone better having any kind of doubt, you can ask. No one? Everything is clear? Right. Now, let's move to the next thing, that is violation of octet rule. Some of them does not follow octet rule at all, right? So, as a general perception that octet rule is acceptable to most of the cases. However, the octet rule is also in significant number, right? Also, the octet rule is violated in also in a significant number of cases. For example, now in this case we know that Be and boron, right? Beryllium and boron have a less than 4 electron, right? Valence electron, because we know that beryllium having electronic configuration 4, so it having only 2 comma 2, that is 2 valence electron, and boron having electronic configuration 5, it means they have a 2 comma 3. Okay, so beryllium and boron have a less than 4 valence electron, hence their octet cannot be completed even they bind with the full strength, right? It means if the beryllium make two bond with the two valence electron, then also their octet is not complete. Same for the boron. Boron, if they form with the full strength, like if they make bond with the three valence electron, then only 6 electron they get, right? So their octet is also incomplete. So we can observe here in case of BeF2, total 4 electrons in octet are present only. Similar in the case of BF3, total 6 electrons are present in the boron. So these are the violation of the octet rule. These compound does not follow octet rule. These does not follow, does not follow octet rule, right? So they does not follow octet rule. I hope this is clear to you. Why they do not follow octet rule? Because they have an electron less than the 8 electron in their valence shell, right? And they have an incapable of forming 4 bond because they have only 2 electron or 3 electron in their valence electron. So the element having less than 4 electrons in their valence shell, they do not follow the octet rule. Okay. Now, in a molecule with the odd number of electrons, right, the octet rule is not satisfied for all the atoms. Example, in the molecule like NO, NO2, ClO2 negative, as they have a two center, 3 electron bond. How we can understand this thing? Let's see the example. If I'm talking about NO, right? If I'm talking about NO, so we know that N having 2 comma 5 electrons, right? And oxygen having 2 comma 6 electron. So oxygen required 2 bond, right? So if the nitrogen is giving 2 bond, then also nitrogen having valency 3. So the valency of nitrogen is not completed. Here you can say see that clearly that oxygen, yes, it's good. Oxygen had completed their octet, but what about the nitrogen? Nitrogen is still incomplete because we know that in double bond it will form 2 to 4, 4 to 6, and 1 7. So one electron is still left, right? So nitrogen is here NO N2. In NO, nitrogen is incomplete octet. The octet is not complete. So if the molecule with the odd number of electrons, just like the NO, nitrogen having the odd number of electrons, like 7 electrons, so the octet rule is not satisfied for all of the atoms. Similarly, if I'm talking about NO2, so in NO2 also we know that N form oxygen with double bond. Now N left with the 3 electrons. Out of 3 electrons, it will donate 2 electrons, so they having positive charge. So the in both the above cases, there are total 7 electrons in the nitrogen octet. So their octet is also not completed. So these are the limitation of the Lewis rule, in which the odd number of electrons, the octet rule is not satisfied for all the atoms. Okay, I hope this is clear to you. Good. Now, in the number of compound, there are more than 8 valence electron present in the central atom, right? So various compounds are there in which more than 8 valence electron are present in the central atom. So in a number of compound, there are more than 8 valence electron present in the central atom. This is termed as expanded octet. So this is known as expanded octet. So if they less than 8 electron, also they do not follow the octet rule. If they having more than 8 electron also, then they do not follow octet rule as well, right? So if in a compound, in a number of compounds, there are more than 8 valence electrode present in the central atom, and this is termed as a expanded octet. Now, this tendency is seen in element beyond the third period of the periodic table, right? And if you move below the third period of the periodic table, like in case of sulfur, in case of phosphorus, or we go down there, they have a vacant d orbital, right? And this vacant d orbital allow us their d orbital for the bonding, right? So obviously, octet rule is not applicable in such cases. Some of the examples such as SF6, PF5, H2SO4. So these are the example. In PF5, they're making 5 bonds. So they're having 8, 10 electrons. So more than octet. Similar in SF6, they have a 12 electrons. They have more than octet. Now in this H2SO4, they're having 12 electron, right? So they also having more than 8 electron, and they are termed as expanded octet. Right. So these are some limitation of octet rule. Those having more than 4 electron and belong to the third period or below third period, they do not follow octet rule. Because they have expanded octet. And similar for the element having less than 4 electron in their valence end, like beryllium and boron, they also do not follow octet rule because they have a deficiency of electron in it, right? Okay, now let's see the next thing. Wait. Just wait for a minute. Okay. Now, what is resonance? Because we already discussed in case of O3 and CO3 carbonium ion, resonance comes into the picture. So it is often seen for the same compound like benzene, carbonate ion, that a single Lewis structure is inadequate for the representation of their molecule, especially for explaining all of its property. For example, if I want to explain the property like, we know that in case of CO, right? So in case of CO3, they having a structure like this, right? So if someone asks what is the bond length of CO in CO3, so if someone asks the bond length of all CO bond in the carbonium, are they same? Are they different? Because in general, we know that double bond is shorter as compared to the single bond, right? So as the percentage as character increase, bond length is also decreases, right? So if I'm talking about the double bond having more as character, right? And triple bond having more. So as the number of s character increases, bond length also decreases. So we know that double bond is a shorter, single bond is a bigger and all. But due to resonance in carbonium ion, or we say in case of benzene also, because in benzene also now we get the alternate double and single bond, right? So if someone asks, so what basically is, we know that double bond is a shorter as compared to the single bond, but due to the resonance, they all bond in benzene of between the carbon carbon are same. Similar in case of carbonium ion, that is a carbon oxygen, all bond, whether it is a double single, they all are equal because they show resonance. This double bond is temporary. They delocalize. Sometimes they comes to this point, sometimes they come to this point. So they are delocalized in nature. So better we can represent like this, like O, O, and O, and this is dot like structure, right? This means they show partially double bond character, all the bonds. So all the bond length are equal. So I hope you understand this thing. What is the importance of resonance here? Right. Now, then many structure with the similar energy, position of nuclei, bonding and non-bonding pairs of electron are drawn with the condition that each of these will explain some properties of the compound. These structure are called resonating structure, or we say chemical form, and the hybrid of this structure is considered as the real structure of the compound. Like, for example, carbonate ion in resonance hybrid of the following conical form, just like जैसे मैंने इसको draw किया है, right? So I hope you understand this thing. What is resonance and why they are coming to the picture? Yeah, you can see here as well. This is the chemical form or resonance hybrid diagram of carbonium ion. This dotted line clearly state that these double bond are delocalized in nature. Yani presence of double-headed arrow between the resonating form symbolize resonance. This is known as resonance. Now, from the concept of resonance, the important conclusion what we get is from the concept of resonance, the bond order of the molecule or ion is calculated. So if you want to calculate the bond order of the particular molecule or ion, then you can easily calculate it by using the concept of resonance. How, beta? देखो, we know that how to calculate bond order. So bond order is basically total number of bond between the two atom in all the direct structure, right? That is the total number of bonds between the two atom divided by the total number of conical form, or we say resonance form, right? Let's see some example through which we can easily calculate this, right? So how will you calculate this, beta? So in this, chlorine react with hot and concentrated NaOH and produce compound X and Y. Now, compound X give white precipitate with silver nitrate solution. What is the average bond order between Cl and O atoms in Y? So, first of all, you remember this thing. What happened when the chlorine react with NaOH? So, whenever the chlorine react with NaOH, that is the Cl2 is react with 6 NaOH, it will form 5 NaCl plus NaClO3 plus 3H2, right? And this 5 NaCl is again react with HNO3 to form AgCl. So here Y is nothing but NaClO3, that is Na plus or ClO3 negative. So what is the structure of ClO3 negative? This is the main point here, right? So ClO3 having the structure like this, they show resonance. So how many resonance diagram they having? They having two resonance structure, 1, 2, and 3. So this to this, and this. So they having a 3 resonance diagram. So Cl bond order, that is the number of bonds. So number of bonds they form 2 to 4. 1 bond, 2 bond, 3 bond, 4 bond, and 5 bond. So total number of bond between Cl and O is 5 and divided by the 3. Total number of O surrounding the atom. So this is equal to 3, right? So this is how you can actually calculate the bond order by using the concept of resonance. I hope this is clear to you all. Right? Okay. Shall we proceed now? Good. Now, the one important topic is also here is that is a formal charge. How will you calculate the formal charge? Basically, the atom of a molecule or ion are usually neutral and carry no charge. However, for some purpose, such as to find the reaction mechanism, assigning a formal charge of atom in a molecule or ion is important. Thus, we can calculate the formal charge as formal charge is nothing but is equal to V, that is valence electron. This V terms as valence electrons. So valence electron, this Lp represent the lone pair. Lone pairs of electrons. And this Bp represent bond pair. Done. So this is all about. So how will you calculate the formal charge, beta? Formal charge is nothing, but it is equal to valence electron minus my lone pair plus half bond pair of electrons, right? So this is the way to calculate this. Now, for example, if someone asks how to calculate the formal charge of O atom in the ozone molecule, then how will you calculate formal charge? So we can calculate, as we know that in case of ozone having a structure like this, right? So ozone having a structure like this is oxygen 1, this is oxygen 2, and this is oxygen number 3, right? So they having 6 electron, they having 4 electrons. We already draw this, right? So no need to. Okay. So if someone say calculate the formal charge of oxygen number 1, right? So if you have to calculate the formal charge on oxygen number 1, then how we can calculate beta, right? That is the formal charge on oxygen number 1 is nothing but valence electron. So valence electron of oxygen, we all know that is 6, minus lone pair of electrons, that is 4, right? Plus half into number of bonds. So here the number of bonds, that is, it will form 2 bonds, it is 4 electrons. So 4 and this. So it comes out to be 6 minus 4 plus 2, that is 0. So the formal charge on the oxygen number 1 is 0. Similar, if you want to calculate the formal charge on oxygen number 2, how will you calculate beta? Again, valence electron is 6, lone pair of electron is 6, plus half into number of bond, that is 2, that is 2 plus 2. So it comes out to be 6 minus 7, or we say it's equal to minus 1, right? Similar in case of oxygen number 3, how will you calculate? For oxygen number 3, we know that valence electron is equal to nothing but 6. Again, lone pair of electron is equal to 2. And number of bond they form is equal to 1 by 2 into 3 bond, which is 6 electrons. So 2 into 3. So this comes out to be 6 minus 5, which is equal to 1. Right. So oxygen in ozone molecule, each oxygen atom show three different, like oxygen number 1, oxygen number 2, and oxygen number 3. They show formal charge. Oxygen number 1 show 0. Oxygen number 2 show minus 1. Oxygen number 3 show plus 1. So these are the formal charge in case of ozone molecule. I hope this is clear to you. सबको समझ आ गया होगा, है ना? Good. Okay. So you have to calculate the formal charge of each atom in the sulfuric acid is equal to. So formal charge of each atom in the sulfuric acid. So let me draw the structure of sulfuric acid. That is S double bond O, S double bond O, OH, OH. So this is H2SO4. So you have to calculate the formal charge of each atom in the sulfuric acid. So if you want to calculate the formal charge of this oxygen, right? So this oxygen, that is oxygen number 1, this and this having same, and this oxygen and our equation, that is third and fourth, they show the same number of formal charge, right? And so let's calculate the formal charge of oxygen 1 first. So the formal charge valence electron is 6, right? And here we can observe that they having two lone pair, right? One making bond with the sulfur and one making bond with the hydrogen. So 2 electrons are involved, 4 electrons are still left. So this is 6 minus, and number of lone pair of electron, that is 4, plus half. Number of bonds they form beta 2. One with hydrogen, one with sulfur. So that is 6 minus 5. That is equal to 1. Right. So it will show. Let me. They will make one bond with H and one bond with sulfur. That is 4 now. So 2, the 4 to 6, so it will having charge 0, right? So it will having 0 charge. 6 minus 6 is equal to 0. Similar, if I calculate oxygen number third, because oxygen third and fourth are same, oxygen 1 and 2 are same. So for the third one, we have to calculate the oxygen. So we know that they having 4. So number of valence electron is this, lone pair of electron this is, and this is 1 by 2 into 4. So again, this will be 2. So 4 plus 2, 6 minus 6, again that is 0. So they show 0. So oxygen number 1, oxygen number 2, 3, 4, they also 0 formal charge. Now we have to calculate for the sulfur. So sulfur having valence electron, again formal charge for sulfur. So again, sulfur having valence electron 6, lone pair of electron having no, plus half into number of bond they form. That is 1 bond, 2, 3, 4, 5, 6, 6 to the 12. So 2 and 6, right? 2 and 6. So again, 6 minus 6 is equal to 0. So in each case, we can observe that the formal charge of each atom in sulfuric acid is equal to 0. Right? I hope this is clear to you. Clear है सबको? Anyone having any kind of doubt, you can ask beta. Right. So I hope you will understand this question and there's no doubt in this question. Okay. Now let's move to the next thing, that is hybridization. So this play a very important role also. What is hybridization and all? So what is hybridization? This process involves the mixing of orbital of almost similar energy belonging to the same atom to form the same number of orbital of exactly equal energy. So this process basically involves the mixing of orbital of almost similar energy belonging to the same atom to form the same number of orbital. The new orbital form are called hybrid orbital. This phenomena is actual sense involve redistribution of energy. So sometime hybridization may also define as the redistribution of energy. Now, what are the silent features of or the rules of hybridization? So let's say that some rules, or we say the silent feature of hybridization. The first one is only the valence and atomic orbital of an atom or ion can mix together to give the hybrid orbital. So there is nothing to do with the innermost electron and all. Only valence and electron atomic orbital of an atom or ion can mix together to give the hybrid orbital. Now, the atomic orbital of an atom of a given molecule or ion which participate in the formation of pi bonds remain excluded from the hybridization process, right? It means, what does it mean, beta? The atomic orbital of the atom, molecule or ion which participate in the formation of pi bonds remain excluded. So the pi bonds here are excluded from the hybridization process. If the central atom of the given molecule or ion also has one or more lone pair of electron, then the atomic orbital having lone pair of electron is completely filled orbital or also take part in the process of hybridization. Now, in a few cases, empty atomic orbital are also involved in hybridization, just like B2S6. We are going to discuss this thing as well. The hybridized orbital have exactly equal energy with identical size, shape, and hybrid orbital are degenerated. So degenerate orbitals are the orbital they have the same amount of energy. They are called hybrid orbit. Okay. Now, so the type of hybridization, as we can see, there are the various type of hybridization, like sp, sp2, sp3, or we say dsp2, sp3d, sp3d2, and d2 sp3, right? So sp3d2, and this one is d2 sp3. Let me write here D2 sp3, right? So sp3d2 or d2 sp3, or we say sp3d2. So these are the type of hybridization that can be of the format. Now, out of these, first three are described here in detail. So let's see the first three, because these three are only very much important. So you learn how to find the hybridization. So I hope it is understood that what is hybridization, what is the silent feature of hybridization, which orbital take part during hybridization, which does not take part during hybridization and all, right? So method of identification of hybridization in the molecule. So there is a two method basically. The first method is very simple. Write the electronic configuration for the outermost orbit of the central atom using boxes, right? Now, find the oxidation state of the central atom. Excite the electron from the orbits of higher energy in such a way that the total number of unpaired electron is equal to oxidation state of the central atom. Always remember this thing. Find the oxidation state of the central atom. This is the first requirement. And excite the electron from the orbit from lower energy level to the higher energy level in such a way that the total number of unpaired electron is equal to oxidation state of the central atom. Now, let's see with the following example. In case of SF6, right? So let write the electronic configuration of sulfur. So we know that sulfur having 1s2, 2s2, but just write the electronic configuration of valence electron. So we know that having 3s2 and 3p4, right? So we can fill 3p4 like 1, 2, 3, and this 4. So sulfur atom are in ground state. Now, we know that the SF6 as having oxidation state of S6 work in SF6, oxidation state of S is x minus 6 is equal to 0, or we say x is equal to 6, right? So sulfur having plus 6 oxidation state. So excite the electron from the lower energy level to the higher energy level such that it is the number of unpaired electron is must be equal to oxidation state and not more than this. So here we can see that there is a, if we excite this electron will go into this cell, this electron will go into this cell, that will become 1, 2, 3, 4, 5, and 6 unpaired electron, which is equal to the oxidation state. Now sulfur atom in excited state, they form pairing and form the hybridization like sp3d2, because one orbital of S takes place, three orbital of P and two orbital of D take part. So the geometry is octahedral molecule resulting from sp3d2 hybridization of the central atom sulfur. Dotted arrow represent the electron supplied by fluorine atom. Right? So I hope this is clear to you. How will you find the hybridization? Similar. On the same basis, can you find, so let's see the some more example. For example, IF7. So IF7, we know that the valence electron is 5s2, 5p, 5p, what? 5p, 5, like 5s2, 5p, 5. So this is, so we know that in IF7, I having the oxidation state of +7. Right. So XI, number of unpaired electron is equal to the oxidation state. So it will be equal to 1, 2, 3, 4, 5, 6, and 7. So iodine atom is an excited state, it will form sp3d3. So the geometry is pentagonal bipyramidal geometry of IF7 molecule, resulting to form sp3d3 hybridization of the central atom. Now, what the dotted arrow represent? Electron supply by the fluorine. Right? So I hope this is very much clear to you. Right? Let's see the second method, right? So what is the second method here? So the second method is nothing but this type of hybridization undergone by the atom ion in the given molecule or ion depend on the sum of the sigma bond pair and the lone pair. So this one is very important. So by using the steric number rule, we can find the hybridization, that is number of sigma bond plus lone pair of electrons. Right? So this is the steric number rule. So how we can find the hybridization using the steric number rule? So we can find the hybridization by using the steric number rule, such as number of sigma bond plus lone pair of electron. Right? So this is how we can find. Similarly, for the sum equal to 3, 4, 5, 6, 7, the central atom undergo. If the sum comes out to be 3, then it will undergo sp2 hybridization. If the sum comes out to be 4, then it will go sp3 hybridization. If the sum is equal to 5, then it will undergo sp3 dehybridization. If the sum is equal to 6, it will go sp3 d2 or d2 sp3 hybridization. If the sum is equal to 7, then it will go sp3 d3 hybridization respectively. Right? So this is another method, and this is the very short wave method, right? You can find hybridization of the any molecule within a second by using such method. Just calculate number of sigma bond plus lone pair. Now, along with this, dsp hybridization is also seen in which the 1d, 1s2p orbital combine to hybridize. The shape of the molecule is square planar with the bond angle of 90 degrees. Now, what is this valence shell electron pair repulsion theory? So this one is going to be very, very important because we already studied the hybridization now. So this is going to be very interesting. What is valence shell electron pair repulsion theory? So what is the main postulate of this theory? So let's see the main postulates of this theory. So the main postulate of this theory are the central atom in the molecule contain two types of electron pair. These are bond pair and lone pair. So the central atom in the molecule contain two types of electrons pair. One is bond pair and another is lone pair. Now, the shape of the molecule is determined by the repulsion between all the electron pair present in the valence shell. So the shape of the molecule comes out after the considering all the repulsion between all the electrons present in the valence shell. A lone pair of electron takes up more space around the central atom than a bond pair. Remember this thing. Since the lone pair is attracted by only one nucleus, while the bond pair is shared by the two nuclei. We can understand this thing in a well, right? Because the lone pair, lone pair, if a lone pair is present in nitrogen, it means this lone pair is attracted by only the nucleus of the nitrogen. But if the lone pair is present between the NH and NH, so this is, they are also having electrons, they are also having electron, but these electrons are attracted by their nuclei as well, right? So in this, there the two nuclei comes into the picture, but the lone pair is attracted by only one nucleus. That's why lone pair of electron takes up more space around the central atom than a bond pair. Now, thus, the presence of lone pair on the central atom causes slight distortion of the bond angle from the ideal shape, and which is calculated from the hybridization. So the presence of lone pair of the central atom cause slight distortion of the bond angle from the ideal shape calculated from the hybridization. Right? So what is the repulsion order beta? Just remember this thing. This is very important. So this is the order of repulsion. So the bond pair repulsion is dominated by bond pair, lone pair, and this is further dominated by lone pair and lone pair. So the repulsion is more in lone pair and lone pair, then after lone pair and bond pair, and last bond pair and bond pair, right? So but you must remember the this repulsion order, right? In case of ammonia, later we can say as well, like NH3. So NH3 having a structure like this, and they having sp3 hybridization. Because how we'll calculate this beta? There is a 3 sigma bond plus one lone pair. So we know that when the sum is comes out to be 4, it is equal to sp3, right? Good. So here we can observe that there is also repulsion present, right? There is also repulsion, and they want to increase the angle because bond pair repulsion is also. But here their lone pair is also present. So here lone pair and bond pair repulsion, and due to this repulsion, this bond angle is reduced to 107 degree instead of 109 degree. So expected bond angle in case of ammonia is 109 degree because it undergoes sp3 hybridization, but actually it comes out to be 107 degree. Why? Due to presence of lone pair. And we know that lone pair bond pair repulsion dominated over bond pair and bond pair repulsion. Right? I hope this is clear to you. Good. Now, the magnitude of repulsion between the bonding pair of electron depends on the electron activity difference between the central atom and the other atom. It means the magnitude of repulsion between the bonding pair of electron depends upon the electron activity difference between the central atom and the other atom. Double bond cause more repulsion than the single bond, and the triple bond cause more repulsion than the double bond. Now, this chart is very, very important, and try to understand this, in a detailed way so that you are able to know the shapes of the various molecule using the whisper theory. So if the steric number is 2, what is the steric number? We already discussed number of sigma bond plus lone pair, which is equal to 2. So if the steric number is 2, then the shape is must be linear. Hybridization is sp, as we can see that, right? So if the steric number is 2, hybridization is sp, and the shape is linear. In this, how many possibilities are there? Now, when only two bond pair are present and there is no lone pair, like AX2, like CO2, we have a BeCl2. So these are having the example of the CO2, BO2, BCl2. These all are the example of such, right? Similarly, if the bond pair is 3 but lone pair is 0, then they are known as trigonal planar, right? So when the steric number is basically 3. So when the steric number is equal to 3, it will form trigonal planar, and the hybridization is sp2, just like this, right? Like they having either 3 bond pair and there is no lone pair like BCl3 and all. So they form trigonal planar. Like this is BF3 beta, not BF2, BF3. Okay. Similar, they have a 2 bond pair and 1 lone pair as well, right? So they will also form such type of structure, right? Like NO2, O3, SnCl2. So they will form like the structure, like this. I hope this is clear to you. क्लियर है सबको? एक लोन पेयर आया तो क्या हुआ, एक भी लोन पेयर नहीं है तो दो केसेस पॉसिबल है ट्रायगोनल प्लेनर के अंदर. Now, the next one is, next one is when the steric number comes out to be 4. So under this, we have a three different cases. Now, when there is no lone pair, just like a CH4, like CH4, ClO4, SO4 twice negative, and NH2 plus. So they having the tetrahedral structure. When the one lone pair comes, and having, I also mention one important note here. When there is no lone pair, the bond angle is 109 degree. As soon as the lone pair comes into picture, in case of ammonia, their bond angle decreases because the lone pair bond pair repulsion more as compared to bond pair repulsion. So it decreases to 1.07 degrees. Now, when the two bond pair and two lone pair are present, this is also we are talking about the steric number 4. But in this, we if we have a two lone pair and two bond pair case arise, right? So they have a V-shaped structure like H2O, H2S, and the bond angle decreases to 105 degree. right? So this is how we can draw. So when the steric number is 2, when the steric number is 3, when the steric number is 4, we get the structure like this. I hope this is clear to you all. In steric number 4, we have a 3 different structure, no lone pair with 1 lone pair with a 2 lone pair. Now, let's see when the steric number is equal to 5. So what happened when the steric number is equal to 5? So we get the shape like TBP, that is called trigonal bipyramidal. So now when there is no lone pair, 5 are bond pair are present only, like PCl5, PF5, SPCl3, ASF5. So they having a structure like trigonal bipyramidal. Now, when we have a one lone pair, right? So when we have a one lone pair, then we get the seesaw like structure, or we say teeter totter, or we say irregular sawhorse or folded square. So this is how we get if we have a one lone pair, right? Like SF4 and TACL3. Similar, if ever we have a three bond pair and two lone pair, then we get the T-shaped structure, like CLF3 and BRF3, right? So I hope you understand this thing. One more case is arise there. If two bond pair and three lone pair are present, right? It means AB2 and wait. Here three bond pair, na? Oh, it's well written wrong. So when the two bond pair and three lone pair, so AB2L3, right? So in this the shape is linear. In this the shape is linear. This is in case of three bond pair. So this is AB3 and this is L2. AB3 and L2, right? And this one is AB4 and L1, right? So let's see in case of how will you draw the structure like linear. So if we have a XeF4, right? So we know that in this four bond pair, Xe having 8 electrons. So 8 electrons, valence electrons. So out of four are involved in making the bond with the F. So two lone pairs. So it will make XeF2, XeF4 belong to SF6, right? They belong to the next one, that is square bipyramidal. So if I'm talking about XeF2, so they having though two bond pair, that is every two, and three lone pair, because eight out of four, two electrons are involving here, and six electron means three lone pair. So this is AB2L3. So what is the shape of this? We know that triangle bipyramidal possesses this shape. So we having a three lone pair. So one lone pair, two lone pair, and three lone pair. So what is the shape? Shape comes out to be XF. So this will become linear. So this is the linear shape, that is XeF2. So in steric number 5, we have a three cases when the first one when there is no lone pair, second one when there is a one lone pair, third one when there is a two lone pair, and the fourth one when there is a three lone pair, right? So just try to remember this. When there is only one lone pair is present, then we get the shape seesaw. When we have a two lone pair present, then we get the T shape. If we have a three lone pair present, then we get the linear shape. Now, similar for the octahedral, that is sp3d2. So, what happened for the sp3d2 beta? When the bond pair is 2 and the lone pair is 3, like AX2L3, we get like I3 negative, XeF2, ICl2 negative, BRF3 negative. These all show this type of a structure, right? And when the lone pair is 1, right? When the lone pair is 1. These are the example of linear, right? And the last one I'm talking. In this XeF2 also like this one. Okay. Next, in case of sp3d2, when there is no lone pair, then it is known as octahedral, or we say square bipyramidal. When the one lone pair is present, they are known as what? They are known as square pyramidal only. If there is no lone pair, square bipyramidal. If one lone pair, square pyramidal. If there is no lone pair, if there is a two lone pair, then it is known as a square planar, because both are having lone pair, right? And they are the example like ICL4, XeF5, CLF5, IF5, BRF5, and PCl6 negative and on. Now, the next one is that is 7, that is called pentagonal bipyramidal, or we say sp3d2, their hybridization. So if there is no lone pair, they are known as pentagonal bipyramidal, right? So this is how actually we can draw the structure of this, right? So I hope this is clear to you. Good. So after doing the whisper theory, hybridization, many of the concept, right, dot structure and all this thing, we are going to solve some numerical, and this numerical were coming in your previous year exam, right? So these all questions are from advanced paper. So these questions were asking in your previous year paper. So let's see and try to understand this question in a detail so that you can able to solve this question. So just read this question very carefully. I'm giving you a 1 minute for this question. Try to learn this question, right? And solve this. I'm going to explain after 1 minute. So we have a 1 minute for you. Try to understand this question, right? Right? So anyone? Sure. So I read the question for you. Consider the following compounds in the liquid form. So O2, HF, H2O, NH3, H2O2, CCl4, CaCl3, 6 6 Cl. When charge COM is brought near their flowing stream, so this is the COM, this is a charge COM. They are already charged and brought near their flowing stream. How many of them show deflection as per the following figure? So we know that only polar molecule, because polar molecule having some positive or negative charge. So if the comb is positive charge, then the negative pole is get attracted towards it. If the comb is negative charge, then the positive pole get attracted towards it. So only the polar molecules will show this deflection. So out of the given option, just try to understand, try to separate the polar molecule. O2, we know that O2 is a non-polar molecule. The O2 is not correct. Now HF, yes, HF is a polar molecule. They have electronegativity difference. They having negative charge. They having positive charge. So they having the polar molecules number one. Next, H2. Yes, H2 also having polar molecule. They having a structure like this, right? So they having also polar molecules. Anyone? Any other? NH3. Yeah. NH3, NH3 having a polar molecule. Yes, NH3 having a polar molecule, right? Na having a negative charge and this H having a positive charge, right? So Na having a polar molecule. On the similar basis, anything more? H2O2. So H2O2, H2O2. So H2O2 having a structure like O, H, O, O, H. So they have negative and positive, negative and positive. So they are also polar molecule, right? So they are also polar molecule. Next one is CHCl3. CHCl3. They are also polar molecule. And the last one is benzene, right? That is benzene, chlorobenzene, we say rather. So this is also molecule. This will require the negative charge, right? Electron withdrawing group. So it will become negative and positive. So these all are the polar molecule. Which one is non-polar? That is O2, CCl4 and benzene. So except these three, all are polar molecule and also deflection towards this comma, right? So which one is correct? How many of the show deflection? So 1, 2, 3, 4, 5, and 6. So out of this, 6 will show the deflection. I hope this is clear to you. Question समझ आया होगा तुम लोगों को इसका? चलो. Now, among B2S6, B3N3S6, N2O, N2O4, S2S2O3, and S2S2O8, the total number of molecule containing covalent bond between the two atoms of the same kind, right? So for this, you have to draw the structure, right? So you have to draw the dot structure for this, because without drawing the dot structure, we cannot predict the covalent bond between the two atoms of the same kind, right? So let's draw the structure of N2O4 first. N2O4, right? So how will you draw the structure of N2O4 beta? This is N, this is N, and this is a bond between N and N. We have a two oxygen, right? So N having three, right? It will form either three bond. So it will form double bond with this and this form coordinate bond, right? Coordinate bond with this. Similar double bond and this the coordinate bond. So this is the N2O4. So this is there's a covalent bond between N and N. So covalent bond right? So there is a covalent bond between N atom, right? So this is how we can actually draw. So in this, there is a covalent bond between N atom. Similar, if I'm talking about the next one, that is the second one, right? The second one is nothing but it is equal to N2O. N2O. So how will you draw the diagram of N2O beta? We know that N2O, N and O. So N having this N, right? So N2O. So in N2O, we know that oxygen will form double bond. This will for if they will form double bond, what does it mean? They're having negative charge, they're having the positive charge, right? Only because nitrogen having only capability to form three bonds now. If they will form four bonds, then definitely they're having positive charge, right? Okay, so this is also when the same kind of covalent bond is present with the same kind of atom. Next, that is H2, H2 and O3. How will you draw the structure of this? Let's see. That is S double bond O, right? And S double bond S. Okay, so that is S double bond O and that is S double bond S. And there's a two OH, that is OH and OH. So here also there is a bond between, there is a bond between which that is sulfur sulfur 4 1 5 1 6, right? So they will form bond like this SSSO. So this is also any more. Let's see the fourth one. That is H2H2O8. H2H2O8. We know that the structure of this is nothing but is equal to double bond O, double bond O, right? Double bond O, double bond O. Now, as 4O are consumed, how many H is it? 2H. So form one OH, OH. So we have a 1, 2, 3, 3, 6. So two oxygen we have. So in this also there is a covalent bond between oxygen, oxygen peroxide linkage is present, right? So total four out of this total four cases like N2O, N2O4, H2H2O3 and H2H2O8. There is a total four way in which there is the same kind of bond between the atoms, right? So this is how we can solve this question. I hope this is clear to you. Anyone having any kind of doubt, you can ask better. No? Everything is clear? Good. Now, solve this question. I'll give you 2 minutes for this question. Try to solve this. Each of the following. Just read this question and try to solve which one is correct answer for this question, right? So I'll giving you a 2 minutes for this question. Try to solve this question till I take some water. Just solve this question. So Now, let's see the solution for this question. What the question asks basically, that is each of, right, that is each of the following options contain a set of four molecules. Identify the options. Options means either it is a multiple option question, right? So more than one option may be correct. So identify the options where all four molecules possess permanent dipole moment at a room temperature, right? All four molecules. So let's see each one. If I'm talking about let's see which will not follow permanent dipole, because we know that for them dipole moment is zero, right? So if I'm considering this B option, right? So in B option, BF3 is present. We all know that BF3 having planar shape, right? BF3 having planar shape, and for the planar molecule, dipole moment is zero. So B is incorrect. Absolutely, B is incorrect. Now let's see some other C. Okay, so C is also incorrect. Why, beta? Because in this BCl2 is there, so they are linear. So for linear molecule also dipole moment is zero. So these two options are absolutely incorrect. So let's see the next one, that is SO2. So SO2, they having the bent like structure, right? So it will show, this will show, this will show. Yes. So option A and option D. So option A and option D both will show permanent dipole moment, but option B and C does not show, because in this planar molecule and linear molecule are present, and we know that for the planar molecule or linear molecule, dipole moment is zero. I hope you'll understand this, right? Now, let's move to the next one. That is the sum of the number of lone pair of electrons on each central atom in the following species, right? The sum of number of lone pair of electron on each central atom. So let's see. In first cases, what they ask the TE BR6 minus 2. So from which group this TE belong, beta? Yes. TE belong to which group? Usaceae Tapo, right? Usaceae, that is group 16. Okay, so it belong to group 16. So we know that 16, they having 6 valence electron. So if you draw the structure of this, it means they having 6 valence electron, right? So they having TE. So they having BR 3, 4, 5, and 6. So they will form 6 bond pair. And how many lone pair are there? Because 2 electrons are there now, so 2 lone pairs are there. So, one lone pair are there, because 2 electrons are there. So this is AB6L1. So they will form in the category of AB7, right? So they will form in the category of AB7. So they having only one lone pair. So it having one lone pair. The first one having one lone pair, right? Next. Next is BRF2 plus. So we all know that BRF having this one, right? So BRF2. So BRF2. So we are having how many electrons? 7. Out of 7, 2 electrons, right? So they are left with the 5. Out of 5, they having one positive charge. It means they having 4 electrons. 4 means 2 lone pairs. So they having 2 lone pairs. I hope you understand this thing, how I calculate this. Right. Now, the third one is SNF. So that is SNF3. What is this? SNF3. Which one is the central atom in SNF3, beta? Can anyone tell me? In SNF3, which one is the central atom? Yes, S. Because S is less electronegative. So this is S. They will form triple bond with N. F, F, F. Right. So S will form triple bond with N, one F, single bond, and single bond. So they having any lone pair of electron? No. So they having zero lone pair. So they having zero lone pair. In the fourth case, that is XeF3. So XeF, F, F. So Xe having 8. 8, it means they have a left with 2,6. 2 comma 8, right? So out of this 8 electron, 3 are taking in bond formation, so they are left with 5, and then one negative charge plus 1, that is 6. 6 means 3 lone pairs. So they having uh, three lone pairs. So they're having three lone pair. So what is the sum of this beta? One lone pair plus two, three plus three, six lone pair. So correct answer for this question is six, right? So total six lone pair is present on the all the central atom, right? So the sum of the number of lone pair of electron on each central atom in the following species is equal to six. So just try to observe such type of question they were asking to you in your in your advanced paper. So for this, you just need to know. In this, we just need a whisper theory concept. Just need how to write the lone pair, how to write the bond pair. Uh, Even you want to use whisper theory at all in this question, right? Just you have to know. Just you know what you do. Just you have to calculate lone pair and bond pair, right? So this is very simple question because they are not asking about the structure, shape, and all. They just ask in this question, identify the number of lone pairs. So if you know the know how to draw the structure of the molecule, then you are easily get to solve this such kind of question, right? Now, the fifth question is this question is also very, very important. Among the triatomic molecule ion BeCl2, N3, N2O, NO2 plus, O3, SCl2, ICl2, I3 negative, XeF2, XeF2, the total number of linear molecule ion where the hybridization of the central atom does not have a contribution from the d orbital. So, right. So only you have to identify the linear. So we know that for linear we have a hybridization like sp. One important note also now in case of sp3d also we have a one case where we get the linear one like in case of xef2. Yeah, we are getting this. So in this question, it was clearly mentioned does not have contribution of the d orbital means you do not have to take this linear shape. So only stick to the sp orbital, not to sp3d. So we know that for sp, for the one is BeCl2. We know this is one is very important. BeCl2. This will show, right? So one is BeCl2. So BeCl2 show linear, right? On the same basis, the next is N3 negative. So how will you draw the structure of N3 negative beta? This is nothing but N, N, and N, right? So this is the bond between this. So these two having negative, negative, and this will become positive. So this is N3 negative. Let's draw the structure of N2O, right? N2O. So this is N, N, this is O. So this is N2O. Now NO2, we all know that for NO2, we draw the structure like this, right? So these all are the linear molecule because in all cases they having hybridization sp. So they having hybridization of sp, they having sp hybridization, they having sp hybridization, they having sp hybridization. They all are linear. I hope this is clear to you. They all are linear. Why they all are linear in nature? Good. Now, question 6, this one is also very important. A list of species having the formula XZ4 is given below, right? So XDF4, SF4, SIF4, BF4 negative, BRF4 negative, CONS34 twice plus, FeCl4 twice negative, COCl4 twice negative, and PtCl4 twice negative. Defining shape on the basis of the location of X and Z atoms, the total number of species having a square planar shape. So you have to identify the total number of species which will show a square planar shape. So it is clearly mentioned XeF4. We already discussed this thing in whisper theory. XeF4 show this structure because we know that it will belong to the category of AB4 and L2, right? So AB6, and we know what is the structure of AB6. Yeah. So they having F, 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 and F. And here X is there. So it will show such kind of a structure like XeF4, or we say square planar. So they will show the structure like a square planar. So XeF4 is a square planar in nature. Similar SF4, so seesaw. So this is not the square planar. Similar SiF4. So silicon fluoride. Silicon having 4 electrons out of 4. So they are also not so. BF4 is sp3 hybridized. They show tetrahedral. BRF4 negative. So they will also not show this. Now, this was whether it will show or not. So this is from coordination compound, right? So we know that from coordination compound, we discussed this thing, right? So this is the case of tetrahedral, and this is a strong ligand. So whenever the strong ligands are there, they will show square planar. That is D2sp3 hybridization. So it will show. So this will show. Now FeCl4. So this is a Cl is a weak ligand. So this will show square tetrahedral, right? So this will not show. Similar COCl4 twice negative and PTCl. So PTCl4 show. PTCl4 show. So there is how many of them show a square planar beta? XeF4 so square planar. And the next is copper ammonia so square planar and the PTCl4. One important one is BRF4 negative. Let's see this thing as well. BRF4 negative. We know that BR1F, 2F, 3F, and 4F. So, and one negative charge. So, 4. So, they're having 7 electrons. So, out of 7, 4, 3, and 4. So, 2 lone pair. So, this is also comes in the category of 4 bond pair, 2 lone pair. So, they will also show this structure. So, out of these 4, that is XeF4, copper, that is a tetra ammonia copper, and the platinum tetrachloroplatinum 2 and the BRF4 negative. They four are show the square planar shape. The total correct answer is 4. Right? Now, based on the whisper theory, the number of 90-degree FBRF angle in BRF5. So in BRF5, you have to calculate the number of, based on the whisper theory, the number of 90-degree. So let me first draw the structure of BRF5 using the whisper theory. So we know that this belongs to the category of AB5 and one lone pair, that is AB6, right? So this belongs to the category of AB6. So what is the structure for the AB6 beta? AB6. How will you write? We'll write like this is BR, this is F, this is F, this is F, this is F, and one lone pair, right? This is also F, and this is the lone pair, right? So we know that each having 90 degree of angle, right? Each having 90 degree of angle. They are asking about the angle between FBR and F, right? FBR and F. This one, FBR and F, FBR and F, right? So what is the angle between FBR and F beta? That is equal to 0 degree, right? Why? Because in BRF5, there are 5 bond pair and one lone pair on bromine atom. Hence, the hybridization is sp3d2. And the shape is also we know that is a octahedral shape. Due to lone pair repulsion, the bond angle are lower than 90 degree, right? So the due to lone pair, due to presence of this lone pair, because if this lone pair is not present, if they are the case of SF6. So let me draw the structure of SF6. In this, there is no lone pair are present, right? So if there is no lone pair are present, it means all the bond angle are of 90 degree. All bond angle are of 90 degree. As soon as lone pair comes into the picture, right? So as soon as lone pair comes into the picture, they start making repulsion. And due to this repulsion only, right? Due to this repulsion only, they start making repulsion. And due to this repulsion, none of the bond is purely 90 degree. So based on the whisper theory, the number of 90 degree FBRF angles in BRF. So you have to say 0. Due to presence of lone pair, the distortion takes place and no one is perfectly 90 degree. I hope you get this. If an SF6 they're asking, then you have to say, yeah, there are total 6 FFs at 90 degree are present. All are present at the 90 degree. But In this case, one lone pair comes into the picture, and due to this lone pair, we know that lone pair repulsion dominate over bond pair, lone pair repulsion, right? So due to this only, none of the bond is perfectly 90 degree. Okay, now let's move to the next question. That is the compound with the two lone pair of electron on the central atom. So you have to identify the compound with having two lone pairs of electron on the central atom. So identify first the compound having the two lone pair of electrons at the central atom. So if I'm talking about BRF5, or already discussed in case of BRF5, they having only one lone pair, right? So they having one lone pair. Already in previous question itself, we draw the diagram for this. ClF3. So we know that Cl having ClF3. So Cl having 7 electrons, so they having two lone pairs, right? So ClF3 having two lone pair. XeF4. So again, XeF4, they having 8 electrons. So they having also two lone pair. The next one is SF4. SF4. They having 6 4. No, they having only one lone pair. So F that is ClF3 and XeF4. So out of only two, that is B and C. That is option B and option C. So B ClF3 and XeF4. They having two lone pairs on the center. I hope is it clear to you, right? This is very simple questions, right? So these questions are very simple. Just try to understand this question. From chemical bonding, you are able to attempt the question. No worries. Just consider on the main fact, that is what is Whisper theory, what is dot structure, what is MOT theory. So if you know these things now, then you can easily solve the question related to the Whisper theory, right? Now, assuming 2s 2p mixing is not operative, the paramagnetic species among the following is. So you have to identify the paramagnetic species among the following, right? And one condition is given, assuming 2s 2p mixing is not operative. So if the 2s 2p mixing is not operative, then what this mean? Then molecule orbital may be arranged in the order of energy, as we know that if the 2s 2p orbital is not orbited, then they are follow the this order, that is sigma 1s, right? Sigma star 1s, sigma 2s, sigma star 2s. This is sigma 2pz. Remember this. If the 2s 2p mixing is not operated, then sigma 2pz comes first. After this, we can write pi 2px, right? This is equal to pi 2py, right? Pi star 2px, pi star 2py. They all having the similar energy. And the last, sigma star 2pz, right? So these are the possible electronic configuration, right? So applying this configuration in case of B2, or we say in B2 or N2 will be the diamagnetic, but C will be the C2 will be the paramagnetic. So this C2, because you have to identify not paramagnetic. So by C2 have paramagnetic, because C2 having electronic configuration of 1:2, 2:2, and 2p2. Right. So if you write this in case of 1:2, 2:2, sigma 2pz, right? So for this, we know that how we'll draw this. Let me draw to show you. So in case of P, we know that P having 3 orbitals. So 2p2, 2p2 means 1 and 2. So this is 1 and 2. So this is sigma 2pz, and this is pi 2px and pi 2py. So this is 4. So 2 to 4, so 2, 3, and 4. So they having one unpaired electron. So one unpaired electron in pi 2px1 and pi 2py1. So due to presence of one electron in pi 2p1, pi 2px1 and pi 2py1. So due to presence of this one electron, they will show they will show this, right? So they will show paramagnetic behavior as compared to B2 and the N2. They all are diamagnetic except C2 because they will show this, right? Okay. The next one is among H2, helium plus Li2, B2, V2, C2, N2, O5, F2, the number of diamagnetic species. So you have to calculate the number of diamagnetic species. So just on the same basis, we know that how will you calculate this? So for H2, we know that sigma 1 H2, right? H2, it means 1 and 2. So sigma 1 is 2, right? So sigma 1 is 2 there. So this is a diamagnetic in nature for if I'm talking about hydrogen. Similar, if I'm talking about helium 2 plus, so the helium having 2 to 4, 4 electrons, right? So it will having sigma 1s, right? So they having sigma 1s1. Similar, lithium 2 plus. So before beryllium 2 plus having 1 sigma, right? 1 sigma, sigma 1s2, right? Sigma star 1s2, sigma 2s2 and sigma star 2s2. So you can draw every structure like this, right? So you get to know the which will having the unpaired or paired electron. So those having two electron in their outermost shell are diamagnetic. Those we have only one electron are called paramagnetic. So if you draw, you'll find the six one. That is which one beta? That is helium 2 plus and the B2 boron plus. And the next is you'll find this in case of oxygen 2 negative, oxygen 2 negative, and which one beta later on you'll discuss. Any all the electrons are paired. So H2, lithium, B2, C2, N2 are the diamagnetic spaces. However, in case of other molecule, right? Like H2, you have to calculate the diamagnetic now. So these only are the para, right? So these are para. So except from all this thing, that is the sixth one, six species, they all show diamagnetic behavior. So I hope this is clear to you, right? Good. So this is all about how will you draw this, right, beta? So this is the way to find the be diamagnetic or paramagnetic character. So today, as we already covered all the important topics and we covered 10 previous questions from the advanced paper, right? So only this type of question was going to be asked from this chapter. So try to learn this, understand and try to learn this concept so that you can able to solve the question, right? So understand this thing. This is going to be very, very, very important for you and learn this because this one is very important and only such type of questions were coming from this chapter, right? So try to understand this thing. So let's meet in the next class where we'll cover thermodynamics. We are starting with the thermodynamics from the next class, right? So we are discussing about the thermodynamics and all. So let's meet in the next class where we're discussing about the thermodynamics. Still, just revise the concept, just read the concept and try to solve as much as numerical as you can, right? Once you start solving, then you feel it's good and you become habitual and try to solve and question become very easy for you. Okay, so